Hello everyone, and thanks for coming to this presentation. I am Guillermo Segura and I will present this brief conference about the influence of the degree of utilization on the structural behavior of stainless steel frames subject to fire. Here are the contents of this presentation. I will start with a brief introduction to stainless steel and its response in front of fire. Then I will show the validation of our numerical model, and at the end I will present the parametric study and discuss the obtained results. Lastly, some conclusions concerning this presentation are pointed out. Nowadays, the use of stainless steel is increasing in the building construction industry. This is because stainless steel shows some advantages compared to carbon steel. Some of them are shown here, like its inherent corrosion resistance, a better aesthetical appeal, high ductility and its inherent strength hardening, better seismic response, and a superior fire performance. This last one is the one that we are interested in. In order to design a stainless steel structure under fire situation, we should address to these European codes, all from the Eurocode 3. Part 1.1 for general rules, the Part 1.2 for fire design, and finally the Part 1.4 specific for stainless steel. Currently, this Part 1.4 devoted to stainless steel does not provide a specific formulation for stainless steel under fire situation, and it refers to the Part 1.2 for fire design, which is based only on carbon steel. Therefore, if we want to assess the real response of a stainless steel structure under fire situation, we need to use advanced numerical model based on the mechanical and thermal properties of stainless steel. Is it true that in the last years it has been studied the response of stainless steel structures under fire, and therefore the upcoming version of the Eurocode 3, the Part 1.4, will include a specific formulation for stainless steel structures under fire. However, this formulation is mostly based on experimental and numerical tests of isolated elements. Therefore, the global response of the structure is not considered, and the possible redistribution capacity of internal forces is dismissed. Before getting more into the topic, first I will introduce the typical response of stainless steel under elevated temperatures. I just said that stainless steel has a better response under fire than carbon steel, but why is that? The first advantage of stainless steel is its thermal properties, allowing it to heat up a bit slower than carbon steel, at least until the 700 degrees, when the carbon steel suffers its first change. The first property can be easily seen with an example. The same rectangular hollow section, shown here, subject to fire in its bottom part, one of carbon steel and the other one of stainless steel. In the left, both figures show the temperature development of each cross-section along the web. As fire starts, it heats up both cross-sections. It can be seen that the carbon steel cross-section heats up a bit faster, at least until it reaches the 700 degrees. Then the stainless steel cross-section starts to equal the temperature field of the carbon steel. This thermal property is an interesting advantage for stainless steel, but the main competitive advantage that the stainless steel has over carbon steel under fire situation is that it has better mechanical properties at elevated temperature. Thanks to its inherent strength hardening, a well-designed stainless steel beam can resist higher temperatures under a certain load. This property can be easily seen with another example, a simple supported beam under a distributed load, like the one shown here. Then the temperature will start to increase uniformly along the beam. Here in the left figure, it will show the evolution of the maximum longitudinal stresses at mid-span, for the carbon steel beam in red and for the austenitic stainless steel beam in blue. Now it shows the initial stresses due to the already load applied. As it can be seen, as the temperature increases, the stresses start to develop until they reach the ultimate stress of each material. Shortly after reaching the ultimate stress, the beam collapses. As it can be seen, the stainless steel beam can resist higher temperatures under the same initial load. But how did we obtain all these temperature distributions and the mechanical response of the beam at elevated temperatures? Well, based on the standardized curve of gas temperature in fire situation provided by the Eurocodes, the ISO 834 shown here, the temperature of the structure can be easily obtained by solving the Fourier's equation, which is ruled by three physical phenomena: convection, radiation, and conduction. Once the gas temperature is known, thanks to the standardized curve, the heat transfer between the gas and the structure can be calculated at each time step, obtaining the temperature field of the structure. When the temperature is known, the mechanical properties are updated at each time step, according to this temperature field, and then the mechanical problem can be solved. Since doing laboratory tests for stainless steel frames under fire is very costly, we opt to develop a numerical model that could assess the response of this type of structures. We had previously reproduced laboratory tests of isolated elements by means of numerical models with good agreement between both results. But since we wanted to analyze the response of stainless steel frames under fire, we looked up at the literature for laboratory tests of steel frames under fire. The most relevant one is the one conducted by Robert and Schaumann in 1986. They test a total of 18 carbon steel frames with different geometries and loads applied. For this study, we only reproduced the one-bay frames. The results obtained by means of our numerical model were in accordance with the results obtained on the test. Thanks to this validation and the ones previously done, we consider our numerical model validated and capable to reproduce the response of stainless steel frames under fire. One of the main parameters that affect the response of any type of structure under fire is the degree of utilization, which is the amount of load applied when the fire starts, compared to the maximum load that the structure can withstand at room temperature. Of course, the structural response of a steel frame subject to fire clearly depends on this degree of utilization. With this in mind, we developed a parametric study centered on double fixed frames with rectangular hollow sections, under the combination of loads shown here, for carbon and stainless steel. Both material properties were obtained from the Eurocode 3, Part 1-2. This combination of loads, distributed on the beam and concentrated load on the right joint, was defined in order to trigger the complete failure mechanism at room temperature, for both carbon and stainless steel Class 1 frames. Moreover, we analyzed the response of a similar stainless steel Class 3 frame in order to compare this response to the one observed by the stainless steel Class 1 frame. In order to solve this type of structures, a geometric and material nonlinear analysis is needed. First, we're going to analyze the obtained results for the stainless steel Class 3 frame. Class 3 structures are supposed to fail once the critical cross-section surpasses the yield stress. I'm going to show one of the analyzed Class 3 frames under fire situation. In this case, the frame analyzed, and the one shown here, is the one corresponding to a degree of utilization of 0.3. The figure in the right will show the evolution of the maximum stress as the temperature increases at the critical cross-section, the right joint. Now it can be seen an initial stress due to the already load applied before the fire starts. Once the fire starts, the frame starts to expand due to thermal dilatation. Then the stresses start to develop, and after surpassing the yield stress, the frame collapses. The frame fails due to local buckling after surpassing the yield stress as expected. All other Class 3 frames analyzed under different degrees of utilization fail, describing a similar behavior. In addition, we can observe that the frames subject to a degree of utilization of 0.7 and 0.6, the ones that are highly loaded, are already surpassing the yield stress before the fire starts, leaving them in a very bad shape to cope with fire. We have seen that the stainless steel Class 3 frames fail as expected, but what about Class 1 frames? Do they really have a certain capacity to redistribute internal forces at elevated temperatures? Well, let's check it with some of the results obtained. Here are the stainless steel and carbon steel Class 1 frames, considering a degree of utilization of 0.3. In this case, since they are Class 1 frames, we'll have to check 4 critical cross-sections at the same time. Yes, in order to develop the presented global failure mechanism, 4 plastic hinges should be formed. Remember that both frames shown here are double fixed frames. Here are the cross-sections that we should check are marked with a number, and each graph are marked with the corresponding number. Each graph will show the evolution of the maximum stress at each cross-section, while the temperature increases. In green, we'll be showing the austenitic stainless steel, and in red, the carbon stainless steel frame. The black continuous line are the lines corresponding to the yield stress of each material, and the dotted line is the ultimate stress of stainless steel. It can be seen that the initial load is already applied, and therefore there is a certain stress in each cross-section. It can be seen that the both right cross-sections, the number 1 and 2, are the ones highly loaded at the start of the fire. Now the fire starts, and internal forces are being induced, reaching the yield stress rapidly on both right cross-sections, on cross-section 1 and on cross-section 2. Then the redistribution of internal forces appear until failure is reached. It can be seen that as in the cross-section 1 and 2 the stresses reach the yield stress around the 600 degrees, the left super cross-section, cross-section number 4, sees its stress increase rapidly, proving that in fact this type of analyzed class 1 frames have a certain capacity of redistribution, even at elevated temperatures. A similar response happens for all different degrees of utilization that we have analyzed. In fact, the figures on the right show the stress evolution of the most stressed cross-section, the cross-section number 2, the right zone, and the least stressed cross-section, cross-section number 4, the left super. The upper figures are for stainless steel, while the lower figures are for carbon steel. As it can be seen, for higher degrees of utilization, the initial stresses are higher. Another interesting fact is that as the initial load increases, the critical temperature is lower, as it was expected. But the most interesting result is that for very high degrees of utilization, the most critical cross-section, the cross-section number 2, for stainless steel and for carbon steel, is highly plastified, meaning that the initial configuration of this frame under fire situation is not a fixed frame, but maybe is a frame with a plastic hinge, which may totally change the response of the structure in front of fire. Finally, this slide shows the main conclusions to this presentation. First of all, both carbon and stainless steel class 1 frames show a great capacity of redistribution of internal forces at elevated temperatures. Moreover, the analyzed stainless steel frames seem to have a better response under fire, unless a very high degree of utilization is considered. Regarding this main topic of the presentation, the degree of utilization, we would like to point out 3 highlights. First, the degree of utilization has a direct influence on the critical temperature and time fire resistance of the analyzed frames, as it was expected. Second, that it can modify the initial structural configuration of the frame for very high initial loads, as it was shown in the last slide. And the last one is that the critical temperatures seem to follow the reduction factor of the material properties. This can be seen with the right figure, that for example, the carbon steel frames clearly follow the yield stress reduction factor, the right line. The stainless steel class 3 frames also follows the yield stress reduction factor, in this case the blue line. Whereas the critical temperature obtained for the stainless steel class 1 frames are between the lines representing the yield stress reduction factor and the ultimate stress reduction factor of stainless steel, between the blue and the green lines, proving that in fact the stainless steel frames are using up part of its inherent strain hardening even at elevated temperatures. This is a very interesting topic that we are currently working on it. Thank you very much for your attention.